Okay, so welcome to this course. I should try with a nice introduction, like we should do it. And you all, now I'm talking about Italian students. I think you have all followed, or most of you have followed the course Reinforced Concrete with me. Some of you not, perhaps, because I can't see or can't recognize all the faces. But it doesn't matter, of course, because the content was more or less the same. And the only difference that in the course that I taught last year, I was using slides written in English, but I was talking Italian. You know, that was a slightly difference. That year, I'm using slides written in English, and also talking English, which makes perhaps a little more complex. But on the other hand, what I want to say is that most of these words that you can find here in English, perhaps they have an easy translation in Italian. If some of them are a little more complex, then I'm going to tell you what is the right translation. I mean, if you talk about macrostructure, I think there is no need to translate because it's almost like Italian, except the pronunciation and perhaps the spelling. So, for example, some timber, we will translate like legno segato, which means legno massiccio, we will talk in Italian. In English, it's either solid timber or some timber, they are synonyms basically. So, last week, as you know, I was not here, and on Monday, Dr. Sciomenta gave the first 4-hour lesson. This first 4-hour lesson that you did last week, also the 4-hour we are going to do this today, are very important because they are the real basic of timber engineering. You probably understood last time that timber, compared to reinforced concrete or compared to steel, has two most significant differences, I would say. So if I was to ask you, what is, in your opinion, the most important difference between timber and, let's say, concrete? What would you answer? Did you understand the question? Yes. So what is the most important difference? The most important difference. Voice, homogeneity versus heterogeneity. So concrete is regarded as a homogeneous material, while instead timber is regarded as a non-homogeneous or inhomogeneous material. What does homogeneous mean when we talk about the normal course about structural design, for example? So, sorry, structural mechanics, scienza della costruzione.
Is it same with all directions?
No. So, this is isotropy and anisotropy. So there are two different properties, very different, both very important. One is isotropic versus anisotropy. And this is the second most important difference between timber and concrete, or between timber and steel. So timber is anisotropic, an anisotropic material, which means that the properties depend on the direction where they're measured. So it's not the same if I take a piece of wood, also not a piece of solid wood, but if I take, okay, this is not really wood, this is called laminated veneer lumber. It's a wood-based material, but it's more or less, pretend that this is wood. It's not the same if I pull this material this way, or if I pull it the other way. It's completely different material, as we will see today. But you already seen it last week. This is isotropic versus anisotropic. Okay, this is the first important difference. And the second one, as you said, homogeneous versus non-homogeneous, heterogeneous. So homogeneous means, what does homogeneous mean? If I was to ask you, actually, if Professor Longo was to ask you, what does homogeneity mean for a material?
That the same property, physics property
the material has exactly the same properties in its volume. So the properties do not depend on the point. This does not mean that the properties are the same in all the direction. I may have a homogeneous material with anisotropic behavior. For example, this material here is called laminated veneer lumber. In the end, here, the material could be regarded as homogeneous, this one, because it doesn't have any significant effect. So this is a homogeneous material. However, it's an anisotropic material, because again, as I said before, the properties are the same all around, But if I pull you this way, or if I pull you the other way, the behavior is completely different. So what we have to do, we really have to memorize and to stamp, I would say, in our brain, the concept of homogeneity versus heterogeneity, and the concept of isotropic versus non-isotropic. All the materials that you studied so far, including concrete and steel, they are regarded as homogeneous and isotropic. All the mechanics of structure that we have studied so far were based on those two properties. So material homogeneous and isotropic. Now we're talking about wood, timber. Wood versus timber. What's the difference between wood and timber? In Italian, we're just talking about legno. In English, there is an important difference between wood and timber. Because wood is a kind of material coming from the tree. I could use wood as a burning material for my fire, for example. While is that timber is a structural material. So timber is used for building a structure. While wood is not used for building structure, or may be used for building, but may also be used for burning. So in English, that's a difference between wood and timber. In Italian, we don't make any difference. In Italian, it's legno, both, if you use for the fire or if you use for structure. Okay? So those concepts, as I said before, they are basic because this is the most important difference between this material and the other one. Last time, so last Monday, you have some question? No. Last Monday, you have been talking a lot about isotropy versus anisotropy. And in order to explain the anisotropic or non-isotropic behavior of wood, a micromodel was shown to you, if you remember. Micromodel of wood is a micromechanical model where you consider the wood as if it was made of a series of straws, so cannucce, taken together or surrounded by a less resisting matrix, quindi immerse in una matrice poco resistente. So from this basic micro model of wood, just remind you something like this. So this is another concept that you really need to memorize and to understand, because from this very basic microscopic mechanical model, you can understand really why the behavior is different in a different direction, and why the properties are different in a different direction, and so on. So please spend some time to really digest this model, to understand this model, because all the timber engineering is based on this microscopic model. It's very qualitative model. I don't think that Martina wrote you any equation, but this one is the key to understand really the behavior of the material. So basically, the main direction and all the other secondary, transversal or perpendicular direction. Quindi direzione parallela alla fibratura, so parallel to the grain, and perpendicolare alla fibratura, so perpendicular to the grain. Parallel to the grain, if you want a property parallel to the grain, you put the substrate 0. Instead, if you're interested in a property perpendicular to the grain, you use the substrate 90, which means 90 degrees between basically the direction that we are interested and the direction of the fiber. Okay? So those are basic concepts that must be known very well. So in this case, you understood, I can ask you now to you, what is in which direction? Okay, well, I already told you the best direction, the direction 0, and the worst direction, perpendicular to the grain. Now, if I want to ask you about the mechanical properties, if we go to measure the mechanical properties parallel to the grain, so the strength parallel to the grain, is there any difference between compression and tension parallel to the grain? Yes. What is best? Tension or compression? Tension. Tension is best. Why is best tension?
Because we see that the resistance in compression
Yes.
is quite half.
Yes. Why is half?
Because
Because of the problem called in English buckling.
okay.
So instability would be. In Italian, stabilità dell'equilibrio.
Come first, that's the
Yes.
from
Yes. Instability of what? Buckling of what? Buckling of the specimen or buckling of something different? Clear the question? Stabilità di che cosa? Stabilità dell'equilibrio del provino o di qualcos'altro? Instability of the fiber themselves. So it's not a problem of buckling of the whole member. If you press something like this, in this way, it's not that the whole specimen is going to buckle. Are the single fibers that are going to buckle separately. So separately we have something like this. Buckling of the fiber. And why do the fiber buckle?
Because they are very
slender.
okay.
Yeah, but why can they buckle? See, because they are slender, but they are in a continuum.
Yeah.
They're not only separate. I'm not going to buckle a straw. The straw, they are surrounded by a matrix, so there is a continuum of solid. It's not single straw. So why is it going to buckle if I have a continuum?
Because it is a slow density of the matrix and then
Yes, because the matrix, we said there is, the fibers are basically surrounded by a very weak and less resistive matrix. So the matrix is the weak point. It's like, for example, if you were to load a foundation pipe. So if you drill a pipe in the ground and then you start loading it, but of course, because often use the pile when the ground is not good. I mean, there's no point using a pile if you have a rock, otherwise you can't even drill it. But if you start loading the pile and the soil is very weak, it's clear that the soil doesn't have the stiffness necessary to put in position, to keep in position the pile. Same thing we have here. The less resistive matrix is very weak and doesn't have the required stiffness to keep this slender fiber into position. Okay, so this is the reason why compression strength is half the tensile strength. Because of course, if we had a matrix with the same property or with much better properties, then we would have this kind of dissymmetric behavior. We would have compression strength exactly the same as tensile strength. It's clear? This is another, I would say, basic concept to memorize. Okay, now second question. Perpendicular to the grain. We understood the perpendicular to the grain, we realized that there is resistive matrix, and so the properties are very poor. Now, when it comes to tension and compression perpendicular to the grain, in this case, what can we say? What is the best, tension or compression? Because if by this and what you told me before, I would say, okay, better tension. Why is better compression in this case?
for the same reasons of the tension around the axis.
For the tension along the axis, we say that the best property is tension, and the worst property is compression. Now, tension perpendicular to the grain. What is the best property?
Compression.
Why is it best? Because it's the opposite of what we were saying before.
Because if we make a tension along the transversal axis,
Yes.
we don't have the same resistance for the matrix because there is not a lot of intermolecular interaction.
Exactly. So the point is, if I pull it in this way, if I pull those fibers apart, what is the strength that comes? Is the strength of the matrix or the strength of the fiber? If I pull them apart. If I pull them apart, if I basically apply a tensile force in this way, if I apply a tensile force in this way, I have this, then I have another one here, then I have another one here, and here in between I have the less resisting matrix. So basically, when I put it this way, it's like having a structure like this, or like having a structure like this. If you remember, I don't know if you, the colleagues from mechanics of structure, they were taught you about the springs, parallel, perpendicular, I think so. So, this one. So what does it mean? It means that when I apply a tensile force, who is going to govern the tensile resistance? The less resistant matrix or the strong fiber?
The matrix.
Why? Because the matrix is the weakest link. The weakest link. So we have, it's like a chain. We will repeat several times during this course the theory of the weakest link, also when we talk about cycling. If you pull a chain, this one is like a chain. If you have a stronger link, which is the fiber, and a very weak link, which is a very poor matrix. So if I pull this chain, the load carrying capacity, it will be governed by the weaker link or by the stronger link? For sure, by the weaker link. So in this case, this means that the less resisting matrix is going to govern the behavior in tension perpendicular to the ground. It's like if you want to have a material very poor, you put in between lots of strong steel or other fiber, but if the material is governed by this less resistive matrix, there is no way in putting other stronger material in the wrong direction. Of course, if I was to put some of those fibers random, that would be completely different. If you think about reinforced concrete, for example, reinforced concrete with, probably you have learned this in the course of reinforced concrete, not with me, but perhaps with a colleague talking about material. Recently, the idea is that in order to get some tensile strength out of our concrete, we can just add some fibers. So we have our concrete a mixture, and we just throw some fibers. Those fibers are thrown in a random pattern. So being in a random pattern, we are almost sure that when we apply a tensile force, there will be at least some of them oriented in the right direction, so parallel to the tensile force. And this way we can get some tensile strength much higher than in the case of reinforced concrete without fiber.
An example of this is the slab.
The?
Slab
Yes. Ixan timber, it's a kind of example of this, exactly. Because in Ixan timber, not at the microscopic level, in the Ixan or CLT timber that you're talking about shortly, not so shortly because we are going very slowly, but it could be a little bit of time. When we're talking about cross-dam, this result is obtained not by putting fibers in a random direction, but by having the whole material at a macroscopic level oriented in a different direction. There are some materials like oriented strength board, for example, OSB, where the idea is to basically distract or to break the microstructure of wood and then to reform another material with those fibers randomly oriented. This way you can obtain a fully isotropic material. But to obtain a fully isotropic material based out of wood, first we need to destroy the wood, which means to break this middle lamella and to have those fibers randomly oriented, and then we can again, with the industrial process, to press and to have a material where those fibers are randomly oriented, and then we get a fully isotropic material. Okay? Good. Now, we said in tension we have the weakest property, resistance. In compression, what is better, the behavior, than tension? are squashed together. So the spindle lamella is in some way is destroyed, but then at a certain point, if we push these pipes together, at a certain point they will be in contact. And then, of course, we can get some strength. Just for your information, compression is best. Just remember that there is at least one order of magnitude of difference between the properties parallel and perpendicular to the grain. So parallel to the grain, we're talking about, as we will see shortly, 80, 100 megapascal, like a high performance concrete in compression. In the direction perpendicular to the grain, we're talking about less than 8, 3, 2, 4, so very low. Sì. Allora, però adesso li vediamo. I will say as a magnitude, an order of magnitude 80 megapascal, parallel to the grain, like a high performance concrete, and from 8 down to 5, 2 perpendicular to the grain. So 10 times less or more in the two directions. Okay? Just to memorize it. Okay, clear so far? Good. Now, so this justifies the problem with, we said, anisotropic behavior. Now we need to discuss about the influence of the defect. So what we said before, the heterogeneity of wood. You learned last Monday that structural wood, or structural timber, I should say, has always some defect inside. You can see here, for example, in the big piece of wood, there are some knots. You remember what are the knots? Knotty. What are they? Huh? Yes, the branch, basically. When you cut your piece of wood from the trunk, the knots are basically the fiber that would try to go outside to reach the branch. Do you remember another important defect? The two are the most important defects, knots, and then there was another defect that was mentioned last Monday.
Direction of the fiber.
Yes, grain deviation, deviazione della fibratura. Which means that our fiber, they are not parallel to the size of our structural method, to the main direction of our structural method. So, probably you have already seen this picture last Monday. The idea is that sometimes, you know, you have a tree, you have the upper part of the tree which is slightly eccentric. The trees are in a very perhaps windy region. So we have a torque moment, you can see here between the wind, the center of application, the result of the wind and the stem. And this kind of stress induce some forces into the fibers, and the fibers, instead of growing parallel to the axis of the stem, they run with a spheroidal shape. So, fibra spheroidale. And then when we go to cut our piece of wood, our plant, then you can see that all the fibers are at an angle to the grain. So grain deviation is basically this angle here, the angle between the main direction of the plant and the direction of the fiber. Okay, the knots we have already discussed before. So, now suppose you got from your trunk one piece of wood like this. Of course, this is a structural wood, so it has some defects, particularly in this case you can see it has some knots. Now think about the strength of this piece of wood. Is it constant? If we're talking about, for example, tensile strength, or could be bending strength, let's talk about tensile strength. Is the tensile strength constant along this direction here? What do you think?
No, because of the defect.
No, because of the defect. What is the influence of the defect? Okay, these defects, we said there are basically part of the branch embedded into the wood. Now, if you go back to here, for example, you see here the direction of the fiber. How is the direction of the fiber with respect to this plane, which is the cutting bed of the plant? Basically, perpendicular in some way. So if I apply here a tensile force, the tensile force will be parallel to the grain here, parallel to the grain here, and how will be the tensile force around the knot? Perpendicular to the grain. What is the tensile strength perpendicular to the grain? I said before. Very low. Almost zero, you can say. You will see it's 1, 2, 3 megapascal as compared to 80. So it's almost zero. So in the end, the influence, how can we study the influence of the knot on the mechanical property of the plant? We can just assume that the knot is like a hole. So basically having a knot here, in terms of mechanical property, is exactly like having a hole. So if we understand this concept, then it's very clear what's happened when we go to measure the strength of, for example, this plant here in the different cross section. So from the very beginning here, you can see there are no knots. That the strength, for example, the bending strength would be maximum, would be good, would be what we were saying before, 80, 90, 100 megapascal. Then we got the knots here. What kind of strength we will have when there is a knot? It's important that knot for the bending strength. Let's talk about bending strength for a moment. It's important to have this knot here for the bending strength in this section. Is?
Bad.
How bad?
Because the fiber.
Very bad.
Yes.
Why?
The
Someone
fiber-
said not so bad.
Not so bad because the knot increase the resistance.
No, the knot decreases because it's like having a hole.
But when the fiber
Yes. Meet
the
the knot.
hit the lid. And
Yes.
then, there is a new stress.
Perfect. Yes. So what your colleague is saying is very true. That here there will be this fiber here will have around like this, and then there will be some stresses perpendicular to the brain. However, in this case, it's not so bad. Why is it not so bad?
Because there is not so much different in with knot.
It's exactly a hole. Why in this case here is not so bad, and I would say that, for example, here is bad, it's worse, or here okay, here for sure is worse. Why? Because we have 3 knots on the same line, so it's like having a big hole. But to have a knot here, or to have a knot here, is there any difference if I'm talking about bending strength?
It's near the border.
It's
near the border.
near the border. So bending strength, we know very well that the most stressed part of the cross section is the one near the border, near the edge of the border. I'm not talking about border, but about edge. Okay? So this is not very representative. This is not partially wrong, I would say. So a knot, the bending strength depends, we will see shortly, the bending strength depends on the position of the knot. If the knot is close to the edges, then the influence is very important. Because it's like having a hole close to the most stressed fiber of my beam. If the hole is in the center, well, in this case I have my knot on the neutral axis, where the stresses are minimum. So it's not so bad. So this what this tells us is that the influence of the knot, it really depends on where the knot is located. It also depends on what kind of stress we are talking about. Talking about bending strength is not the same as talking about tensile strength. If I was now to talk about tensile strength, would it make a difference to have a knot here, or there? Less, But also in this case, we will see it will make some difference, because if I have a knot here in the center, I have mostly compression, because my resisting cross-section here is symmetric. If I have a knot on the board, or close to the board, the resisting cross-section is the same. But in this case, with respect to the centroid of the resisting cross-section, I don't have, like before, pure compression, pure tension, but I have tension coupled with bending. And then I have some stress increases close to the hole. But I'm just anticipating some concept that we are going to see with more calm in a few minutes. This was just to say that, to point out that in a timber beam, because of the defects, the strength is not constant along the membrane. It depends on the location and size of the knot. What we need to really memorize here is that a knot for a timber beam is like a hole. Okay? A knot is not, it's like having a hole. In fact, if you think about it, I don't know, I'm sure you touch sometimes some boards made of wood. If you have a knot, you go there to move the knot, sometimes you will get the knot off the plant. You will get the knot in your hand, because it's so weak, the connection. Okay? So remember that a knot, in terms of the effects on the strength of the material, is like a hole. It's clear? This is another very important concept. Since the knot is like a hole, when I'm going to calculate the strength, bending strength or tensile strength in the different cross-sections, it's clear that I'm going to have different values. You see here, for example, this block here. The value is different, because it depends if I'm going to calculate the strength when there are no knots, only timber, then the resistance is good, or if I'm going to calculate the strength when there is a knot. Okay? It's clear? I go very slowly because those are, as I can repeat, those are the basic concepts of all timber engineering. Okay, now, second question for you. When I'm going to design my timber beam, for example, I'm going to use this timber plank or beam. You see here that I have a variable strength. Which strength should I use in my design? Since the strength is variable, I need to define which strength to use in my design. When I want to use the limit state design, which we learned very well last year or a couple of years ago, I need a design strength. The design strength is related to characteristic strength, you remember well, same partial safety factor, and here there will be also another factor that we are going to discuss later. So the point is, which of these values should I use for my design? Which one is the characteristic in this case? Because you see, the strength is variable along this beam.
And the height of the timber is different.
So, since it's variable, I need to understand where to refer my characteristic strength. Is the maximum? Is the average? Is the minimum? Is less than the minimum? Which value?
Minimum points.
The minimum points. Why not? Why the minimum? Because the minimum points is very conservative. It's only 1% of the minimum. All the other, the timber is much stronger.
Because if it's character, it's character goes up to minimum points, and it's very important for me.
Yes. Unfortunately, for the material, for timber, in a situation like this, we need necessarily to take the minimum value. Because this is going to govern all the strength of the beam. Suppose that this beam is going to be pulled. If it's going to be pulled, it's clear that this is the weakest thing. So this is going to govern the design. And this is a big problem for the material, because you can see from here that most of the material would have the potential to resist much more. But instead, we cannot exploit this potential because of this cross-section here. Very good. Dubbi? So, just to summarize, there is a huge difference between small timber specimens and structural size timber specimens. Are we interested in the discipline in timber engineering in small timber specimens? If you want to build a structure, are we interested in the property of a small timber specimen? No. Tell me what you can do. We are very interested in structural size timber member. So set minimum this kind of section. In structural size timber member, we will always have the difference. So we need to live with the difference. So grain deviation, we said the effect of grain deviation on reduction strength. The larger the grain deviation, the larger the strength reduction. Of course. Again, if the grain deviation is in this way, we have a certain reduction. If there is no grain deviation, we have maximum properties. If you have 90%, 90 degree grain deviation, we have a tension perpendicular to the grain, so very low property. So the larger the grain deviation, the larger the strength reduction. The effect of knots. First of all, reduction resisting cross section. We said the knot is like a hole. So you can see here very well the resisting cross section is smaller because of the knot. Consequently, the sigma that we have in our cross section is higher compared to the situation where we have no knot. First effect. This is not the only effect. Because you can see here, if the same knot, rather than being symmetrically distributed, is present only on one side, the situation is much worse. In this case, the maximum stress is twice as much as before. So remember, it's not only a matter of reduction in cross-section, so not only do the knots reduce the cross-section, they also cause peaks of stresses, like in this case. Because basically here we have pure tension, and here we have tension coupled with bending. And so the maximum stress is twice as big as in the other case. Clear? And then something that some of you told us before, also the knots are always coupled with some grain deviation. Because you can see here that the fibers they have to deviate, and we have some stresses perpendicular to the grain. So overall, the effects lead to reduction strength. So we need to keep in mind, this is, if you want, it's a very simple conclusion. If we have knots, we will get worse properties compared to the same material without the knots. Clear? So, again, summary, anisotropy at the microstructure. So we remember, we can justify the anisotropic behavior of wood by looking at the microstructure. So, strength will depend on the direction. Heterogeneity, which means defects, strength will depend on the size of the specimen. So it's not the same for a small specimen as well as a big specimen. Prima. Perché altra cosa non si vede? Okay, now just to anticipate, when we will come back later, strength of wood is also affected by two other things, just to make it a bit more interesting. Loading rate, so it means that it's not the same if I apply my load in 5 minutes on this specimen, or in 1 second, or in 10 years. So the slower the load rate, the loading rate, the slower the loading rate, the lower the strength. Quindi tanto più lentamente applico il carico, tanto minore la resistenza. Okay? Similar behavior, I'm sure you haven't seen it because we don't study at the university, but I can tell you similar behavior you can find in glass members. So glass has a kind of similar behavior. If you heat a glass, you can get the strength much higher than if you push the glass very slowly. Same thing also for timber. And moisture content. So moisture content è umidità, contenuto di umidità. The higher the moisture content, the lower the strength properties. Okay, so low grade moisture content, this influence will be seen later on. Now we just focus on the influence of the defects again. So this is a summary of the properties of wood, let's say timber. Parallel, perpendicular to the grain, parallel and compression, parallel and perpendicular to the grain. Clear specimen, remember clear specimen, I remind you, small specimen, 80 to 100 megapascal, compression 40 to 50, halfway, like we were saying before, compression perpendicular to the grain 2 to 4, and tension perpendicular to the grain 1 to 2. So this is on clear specimen, so specimen, kind of specimen like this. It's not a real clear specimen, because this is LBL, but anyway, specimen like this. Now when it comes to some timber, so structural timber, what we are interested to, due to the defects, you can see that we have a significant drop in mechanical properties. So the tension drops from 80 to 100 to 10 to 35. Tension parallel to the grain. Perpendicular to the grain drops almost to 0. Compression parallel to the grain reduces to 25 to 40. And compression perpendicular to the grain more or less the same. So as you can see, moving from clear specimen to some timber, we have a kind of the rank of the material properties change. Provino piccolo, primo di questo. So basically, while a clear specimen performs best in tension parallel to the grain, for a some timber performs best in compression parallel to the grain. So for some timber, the best property is no longer tension, but it's compression parallel to the grain. Tension parallel to the grain becomes the second most best property, and then we have compression perpendicular to the grain and tension perpendicular to the grain. So when it comes to some timber, we could say that tension perpendicular to the grain is practically zero. In fact, a good design criterion is always to ignore the tensile strength of wood perpendicular to the grain, because it's too low. It's too low and too unreliable. Even though the regulation will give us a small value. Best property, compression parallel to the grain. Why best properties? Because the defects of the knots and the grain deviation affect much more tension and compression perpendicular to the grain. Sì, in English and in Italian. Okay. I was saying that the nodi affects much more, influenzano molto di più the strength parallel to the grain, so the tensile strength parallel to the grain, la resistenza a trazione parallela alla fibratura, then the compression strength parallel to the grain, che è la resistenza a compressione parallela alla fibratura. And now we will want to understand why there is this different influence. So, we said more significant in tension than in compression, and more significant parallel to the grain than perpendicular to the grain. There is also reduction in module of elasticity due to defects, which, however, is less significant than for strength. So when we move from small specimen to big specimen, we have also reduction module of elasticity, but this is less important. Now, just a small question for you. Why are we interested in modulus of elasticity of timber? I would say also the modulus of elasticity of any material.
The presence in water. Water.
No. Why are we interested in the modulus of elasticity of timber in timber engineering, but I would say also for any material in structural design? Why do we need a modulus of elasticity in structural design?
For the stiffness.
For the stiffness. Why do we need the stiffness?
For the strength.
For
For the strength.
See, are you sure for the strength? Is strength always affected by stiffness?
I don't know.
Not always. When? For instability problem. Good answer. So when we talk about buckling or stability problem, the strength, so critical load, for example, Euler load, is affected by the modulus of elasticity, by the stiffness. Okay, do we need a modulus of elasticity only for this? Or also for some other reason? Or if you want, do we need the stiffness only for predicting the buckling strength, or also for other reasons?
For the strength.
Are we sure? Which bending strength? If you want to test the lateral torsional buckling strength, I don't think you want to say this, but if you talk about the lateral torsional buckling strength, then I agree with you, we need it. But if you talk about just a normal bending strength without any lateral torsional buckling, perhaps not. So is there any other reason in structural design why we are interested in the modulus of elasticity and therefore in the stiffness? Or the deflection? The deflection is part of which kind of limit state verification? Serviceability limit state. So buckling and bending strength are required for which kind of limit state? Buckling and bending strength. We need to know them for which kind of limit state. Ultimate limit state. Instead, stiffness, as I said before, stiffness is useful to calculate serviceability limit state, so vibration control and deflection control. Remember that for timber, we will also see this in the future, while for concrete we could forget more or less about the modulus of elasticity, because hardly ever the deflection govern the design for reinforced concrete structure, let's use high performance concrete. For timber, we will see that very often the deflection, so visibility limit state of deflection, is the design governing criterion. Okay, so we need to design not to get a certain strength, but to get a certain deflection, not to exceed a certain value. Okay? Now, why do defects reduce strength much more in tension than in compression? There are a number of reasons. First of all, there is a larger effect of grain deviation on tensile strength. So, those plots here shows the dependency of the tensile strength of wood on the grain deviation. The second one shows the dependency of the compression strength of wood on the grain deviation. As you can see, the two curves are different. The first, the one showing the tensile strength, is much steeper at the beginning, so it's much closer to a, let's say, bilinear. The second one is much more gradual, it's much closer to a simple line. What does it mean? It means that even with a very small value of grain deviation, let's say 10 degrees, you can see we have a drop of tensile strength of almost 30%. While instead, for compression, the reduction is much lower. This means that the grain deviation affects more tensile strength ultimately than compression strength. That's the first reason. Second reason is that the tensile failure is always a brittle kind of failure, while the compression failure is much more ductile. I think you saw the plots, the sigma epsilon plot last Monday, showing that in tension we have a kind of elastic brittle behavior. So tension, something like this. Compression, instead, we go in this way. So tension is brittle, compression is more ductile. So if you have a brittle failure, you can't have any plastic redistribution. So as soon as you reach your limit value, you have a fracture and the specimen breaks into pieces. In compression it's different, because since you have plasticity, you may have a distribution of forces between one fiber and the other. In compression, we have a better behavior in some respect. So for this reason, in compression, the influence of the defect is not so important like in tension. Okay? Because we can redistribute the limit forces even through the knots. Because I said before, the knot is like a ball, but the reality is not a ball. It's just a simplification. You have some wood inside. So if you compress, this wood some way can a bit plasticize and redistribute the forces. Okay? Last but not least, the so-called size effect. Size effect is called also this way in effetto dimensione, but we call size effect also.
Questo è una cosa, ma il comportamento delle compressioni è dovuto anche al fatto che
You need to force yourself to speak in English, otherwise it's too easy.
the plastic error is motivated by the fact that the S2 straight is the fiber of the S2 straights are not only vertical.
No, they are squeezed together, like we said before. In compression, initially the fibers are spaced apart. Then when you start squeezing them, basically you fail this middle lamella, and in the end you get to a situation where these fibers are basically in contact. And they are strong. So for this reason, this curve keeps going, particularly in compression perpendicular to the grain, and also in compression parallel to the grain, but this is limited in some way by the local ducting phenomenon of the fiber. Okay? So, size effect. What is a size effect? There is a so-called weakest link theory. So when subjected to tension, what we already mentioned this before, if you remember, when subjected to tension, a chain made of a brittle material is as strong as its weakest link. So this means that basically everything depends on the weakest link in tension. Compression is not in this way, because in compression, we said before, we can have a minimum of the redistribution of forces. So in the end, you can say that the larger the value of the member that you are talking about, the larger the probability of finding a defect, and the lower the strength or ultimate stress of the member. So in a material like stone timber, basically, what governs the failure ultimately is not the property of the base material, but is mostly the presence, the size, and the location of the defects. Okay? So it's not the property of the base material, it's the property, is the location, the size of the defects of our material. So the strength will be affected by the probability of finding a defect, the probability of finding a knot in the member. The larger the member, in general, the larger is this probability and the lower is the strength. So this is taken into account by the regulation, for example, by the Eurocode 5, when it comes to calculate the strength of the material, there is a coefficient called KH, which takes into account the size of the cross-section. So the normal standard size of a sawn timber is considered 150 millimeter, while instead the normal standard size of a glue-laminated timber, legno lamellare incollato, is 600 millimeter. So the regulation says if you have the normal size of sawn timber or glue-lam or a larger size, then KH is equal to 1. But if you have a size smaller than the normal size, so for example you have a less than 150 millimeter, less than 600 millimeter, then you can increase the strength with this coefficient, which is not. I mean, for some timber may get up to 1.3, for glue-lam just 10%, up to 1.1. Okay? So there is this coefficient which takes into account the dependence on the strength of wood on the size of the wood, of the cross-section itself.
Can you repeat this, the coefficient?
Yes. The coefficient KH is equal to 1 for members having the normal size, 150 or 600 millimeter, or larger. Equal to 1. It's larger than 1 if the member has a size which is smaller than the normal size. Up to 1.3 for some timber, 1.1 for glue-laminated timber. Okay? Okay, now, when it comes to calculate the bending strength of a timber beam made of sawn timber, like in our case. How can we calculate, how can we define this bending strength? Suppose that we want to calculate the bending strength of this piece of wood, the same that we saw before. What we can do, we could start, and we can write a bit here. So this is our cross-section. Strictly speaking, when we have a timber member subjected to bending, we would have a non-symmetric triangular distribution of stresses because the compression strength is smaller than the tensile strength, and in compression we have some elasticization that in tension we don't have. Okay? So strictly speaking, we should use we should use the plastic theory to calculate, like we've done for reinforced concrete, to calculate the bending capacity of this cross-section. Okay? This will be a little bit complex, however, because first of all, we are not sure that the ductility in compression is very high. If you remember, talking about reinforced concrete, we make an assumption that the steel had an infinite ductility. The concrete, however, didn't have an infinite ductility, if you remember well. In fact, we have to transform this parabolic rectangular curve into an equivalent stress block, and that was a bit complex. Here, we should do something similar because we are not sure about the ductility. This could have a limit. We don't know very well this thing. So this will be the first problem. So for this reason, when we talk about bending strength of wood, we always refer to a kind of conventional stress distribution. Even though the actual stress distribution will be something like this, we refer to a conventional stress distribution where basically we have a barycentric neutral axis, and then we have a bitriangular and linear elastic distribution. So, for timber in bending, for the sake of simplicity, we consider a symmetric bitriangular distribution, and so we use the formula of Navier that you study in mechanics of material. So sigma max will be bending moment divided by second moment of area with respect to the centroid of the cross section times, what we call this one, for example, d depth times t divided by 2, or m divided by wx, where wx is the section modulus, the elastic section modulus. This is called, well, okay, this is basically the distribution of stresses, and this one should not exceed the bending moment, the bending strength of timber, Fm, or according to the Eurocode, this is Eurocode 5, or it's also called modulus of rupture from some other regulations like the New Zealand standards or the US standard. So for us it's Fm, the strength. So bending strength. So this bending strength, I just want to stress this. This is a conventional bending strength. Why is conventional? Because we have calculated this bending strength assuming a linear distribution of stresses, ignoring the plasticization of timber in compression. So this is a conventional bending strength, the one that we always use when we design according to all wall regulation. Ok.
Scusi, vuoi rivedere il concetto in italiano se è possibile?
Come?
Se vuoi rivedere in italiano se è possibile.
Cosa?
Il concetto del diagramma, il passaggio dal diagramma all'altro.
Praticamente il diagramma reale sarebbe questo. Siccome è troppo complicato e siccome non si hanno informazioni sull'attività, per semplicità, convenzionalmente si fa riferimento a un diagramma simmetrico. È una pura convenzione. So, timber engineering, when it comes to do a design for bending, this is the assumption. So the regulation will provide us with some value of the bending strength, Fm. Now we'll see how. Once we know the bending strength, Fm, we will calculate using this Navier formula, the maximum stress, and we will check that maximum stress does not exceed this conventional bending strength. Now, since this is a conventional bending strength, how can we calculate this conventional bending strength? Well, calculation is a bit complex. So we should do some tests. We should take our piece of wood and then do test. However, we will see that the results of the test are affected by the type of load distribution, l'articolo di schema di carico, and also they are affected by the length of the specimen. So, if we, for example, if we decide to test a whole beam, like a simply supported beam with a whole load in between, we wouldn't get the same strength as if we test the same beam with 2 point loads in between, and we wouldn't get the same strength as if we test half of this beam. This is a big problem. Why is it a big problem? Because of the knots. If we had a beam without knots, so a beam without any of those defects, the value of the strength that we would get, this Fm, would be exactly the same if we test with 1 point load, with 2 point loads, a small or long specimen. Wouldn't be any change. However, since we have the defects, since we are defining in a kind of conventional way this strength, the problem is that the value of the strength is affected by load configuration and by the size of the specimen itself. How can we prove this? Well, we can prove it this way. Suppose, for example, that, let's write here something. This is our beam. Suppose that we know the value of the strength of the material itself without the defect. So we know the strength of the clear specimen, so the material without the defect. So this one is, for example, F1. Let's try to use so we don't make confusion the same symbol here. Yeah, Fn1, for example. No, F1 is okay. So we know we've done first some tests. For example, I have a piece like this, and I've done some tensile tests. Okay, it was more specimen without defect. I found this is F1, the strength is F1. Okay, I'm going to think about calculating the strength of this beam in a section like this. A section like this is quite simple. The bending strength, M, it's called M1, will be F1, which is the tensile strength of the material without the defects, times the second moment of area of the whole cross section. This is 1. With respect to the x-axis divided by b half. Okay? So this will be the strength of the solid cross-section of the beam where there are no defects. Right? Now, suppose I want to calculate instead the strength when there is the defect. When there is the defect, I will have a different cross-section. The defect is like a hole. So, I will have M2, so this will be M1. M2 will be F1 times J2x divided by half d, where J2x, second moment of area of the resisting cross-section without the hole with respect to the x-axis. J2 will be less than J1. Okay? And then of course I can do the same exercise in each cross-section where I have a defect, like here. Here I will have a cross-section like this. M3, J3, even less than J2, and M3, F1 times J3x divided by half d. Okay? Clear? Good. Now, What I can do for a beam like this, I can calculate, I can draw the diagram of the resisting bending moment. What is the diagram of the resisting bending moment? It's exactly what you were doing in reinforced concrete design when you were designing the reinforcement. So basically it's the diagram showing in each section what is the actual strength resistance. Okay? So, resisting bending moment. Which value of resisting bending moments I have here? Here I have no defect, so the value would be M1. Okay? Are you following me? Good. Now, first defect is here. Constant. Then when I have this defect, it's basically like this one, M2, I will have a drop of resistance. Here the moment resistance will be a little bit less. So this will be M1, this will be M2. Why will be less? Because I have a hole. The hole reduces my resisting cross section. The second moment of area is a little bit more, it's a little smaller, and so M2 is a little bit smaller. Then again, M1, as far as this other cross section here. Here I have an even larger drop. Why? Because I have two holes, two knobs. So here I will have something like this. And this will be M3. Clear?
Yeah.
Are you following me? Okay. Then I continue. As far as this other knob here, again M2. And then here. So this is what we call the bending moment capacity of my beam. So the bending moment capacity of my beam is not constant. Why is not constant? Because I have defect. If I didn't have any defect, it would be uniform. It would be just this. But since I have some defects, I have this discontinuity here. So this is the bending moment capacity. Okay, now suppose that we are going to load this beam. For example, by 3-point bending. P. How can I calculate now the maximum value of the force P such that I get to the failure of the beam? Well, I start, I know what is the distribution of the bending moment. If I have a point load, it's a triangular distribution, so for a smaller value it will be something like this. So the value of the force P leading to this value here of bending moment is the one associated with failure. So the value of P leading to this maximum bending moment at half span is the one leading to failure. Clear what I've done? This is the bending moment capacity. So this is the M3, basically is the strength. And this is the value of the bending moment associated with P. Is this value of P leading to this bending moment leading the beam to failure? No. Why not? Because lower. Which value of P do I need in order to get to the failure? Well, I need to increase a little bit, just a little bit, in order to get to a situation like this. As soon as this curve here, representing the bending moment demand, meets the curve of the bending moment capacity, so this equation here, then you see when we have this meeting here, then we go to the bending failure. We can't increase anymore the load. Why we can't increase anymore the load? Because we have reached the bending moment capacity in this cross section. Okay?
The second line.
The second line.
I rated the moment.
This is the diagram of the bending moment demand leading the beam to failure. It's like what you are doing in reinforced concrete design. You have the capacity, well, the capacity bending moment associated with this cross section with the reinforcement, and this capacity, if you remember well, should cover the whole envelope of the whole demands with a different load situation. In this case, we have only one load configuration. And so this is the value of the force P leading to the failure of the beam. Note that if we would have a homogeneous material, the value of P would be much higher. It would be the value associated with this kind of bending moment demand. But since we have a defect, and we are so lucky that the defect is actually at mid-span, the value of the capacity. So basically, what I do, I load this beam in the laboratory, I measure P, I measure the PF, the P leading to the failure. The P leading to the failure is the one associated with this bending moment. So I can write moment of failure would be PF divided by 2 times L divided by 2. So this is L. This is L divided by 2. This is L divided by 2. In a beam like this, you know very well from static. This is P. This is P divided by 2. Bending moment. Maximum bending moment here. And max and F is, okay, let's see M. M is P divided by 2 times N divided by 2, right? So I can write that MF, the moment leading the beam to failure, is PF, the load leading the beam to failure, divided by 2 times N divided by 2. Right? You follow me? You still awake? Okay. So this MF, now, with this MF I can calculate the conventional bending strength of my beam. Conventional bending strength of my beam is this one. This is the conventional one. So the conventional one will be Fm. So Fm will be equal to Mf divided by Jx. Jx is this one, J1x, because it's conventional. The conventional is the one calculated over the whole cross section. Okay? I can write here J1x times D divided by 2. So this is the, if you want, this is the limit condition, Fm equal sigma max. Okay? And then of course I can replace here, I can replace Mf with Pf times L divided by 4. Note that this value of Fm is completely different from F1. F1 was the strength, the tensile strength on a clear specimen of wood. Okay? Fm is the conventional bending strength of wood, taking into account the effect of the defects. What would be the ratio between Fm and F1? With F1, you see, the strength would be M1. With F2, with Fm, the strength would be this value here. So F1 would be much higher than the other one. It's clear? Because F1, if F1 is the strength of my beam without any defects. Without any defects, you see, we would get a P F prime much larger than PF because would be the value that would bring me the bending moment capacity, the bending moment demand equal to the bending moment capacity M1. Okay? So this shows us that due to the defects, the conventional bending moment capacity is much much lower than the bending moment, the tensile resistance. Sorry, let's repeat again. Due to the defect, the bending strength of the wood, of the timber, is much lower than the bending, the tensile strength of the wood without any defect. Okay? Now, the important point that I want to show you also is that this value that we found here, so by doing this test, by doing this derivation, we will get, first of all, we will get a value of strength, of course, completely different from the strength of the clear space. So we can see from here the very remarkable effect of the defects on the strength of wood. Second point, this value of Fm that we have obtained in this way is dependent on the load configuration. So on the type of test that we are doing. It's not the same to apply a point load in the middle or to apply, for example, 2 point loads here. If you apply 2 point loads there, the diagram of the strength demand will be different. So it will be something like this. Now, unfortunately, this is going to be a bit crowded, this plot, but so if you have a thing like this, the bending distribution is different. And so, if you do the derivation, you will find that with this different load distribution, you will get also different Fm. You will get an Fm dash, for example. So the value that you would obtain would be different from the one you obtained before. Perhaps now we can see it's clearer looking at the slides right now. And last but not least, if we are going to test not the whole beam, but suppose we want to test only half beam. We cut the specimen in two, and we test separately the two halves. If the material was homogeneous, we would get exactly the same strength, not different, because the strength is not affected by the size of the specimen. But instead, suppose that we are going to test only this part here. What do you think? How would be the strength of this part B compared to the strength of the other part? Huh? Why?
Because there isn't the 2 knots.
Because the 2 knots, before were harm a lot, now they go on the other side. So we will wait only one small knot in the middle. So this specimen here will get an Fm, let's say 2 bar, much higher than the Fm we got before. Because in this case, how would be the the diagram of the bending moment demand if we were to test this specimen here. Suppose we test in this way. So, in this case, the bending moment demand would be something like this. Right?
Are we considering this in the outcome that?
Yes. We cut the specimen in two. We are testing only the right half of the specimen. In this case, we have lost this knot created before the problem. And then you can see this is the bending moment distribution. And this the load here can be much higher because I can get up to, you see, something like this. So we get an FM, let's say 2 bars, much higher than before. Sì, poi lo vedremo anche comunque nel diapositiva, dopo il passaggio sulla lancio. Praticamente abbiamo preso il provino, abbiamo tagliato in due e abbiamo testato, stiamo testando solo il provino di testa. In questo caso, il diagramma della domanda di resistenza è molto più alto. Quindi FM, we can get an FM 2 bar much higher than the FM that we got before. Then what we can do, we can test the other half. The other half, even the other half will be a stronger resistance this time. Why? Because you see, this time, these two knots, they are not in the middle of the span, but they are very close to the support. So, here, we will get, well, so no, sorry, this is wrong. Something like this. So, even in this case, the FM that we got would be higher. Let's call it FM 3 bar, would be higher than FM, but smaller than FM 2 bar. It's clear? So what I would like, I know this is not a simple concept, but what I'm trying to make you understand is that due to the defects, the strength, particularly this conventional strength that we define there, is dependent on the size of the specimen. It's not the same if I test a shorter or longer specimen. It's also depending on the loading of the load distribution. It's not the same if I apply a point load, 2-point load, or uniformly distributed load. Now, since for our structural calculation we need one value of Fm that we can use for any kind of load distribution, any size of specimen, it's clear that when we do testing, experimental testing, we need to, in some way, standardize our test. Because otherwise, if I test a small specimen, we get a better strength. The other university tests a longer specimen, that better strength, we couldn't really do a design this way. So for this reason, there are some standards dealing with timber design, which basically define clearly what kind of tests we should do to calculate the bending strength. Those standards say, first of all, the load distribution should be this. So, the test of wood, test to calculate the bending strength of wood shall be carried out on beams loaded with 2-point loads at the third of the span. This is called 4-point bending distribution, 4-point bending. Why 4-point bending? Because it's 1, 2, 3, 4 points, which define the bending moment diagram. 4-point bending distribution. First rule. Second rule, my specimen should have a slenderness ratio larger than 18. Now, 18 we check it, I don't remember by heart. What is the slenderness ratio? Slenderness ratio is the ratio L over D. Where L is the length of the beam, D is the depth of the beam. So L over D, slenderness ratio should be greater than or equal to 18. If we comply with this test requirements, we are sure that the Fm, this conventional bending strength that you can get, is comparable between different specimens, between different load applications. Ok? Sì, su D deve essere semplicemente maggiore o uguale a 18. Quando faccio il test sperimentale. E in più, 2 forze concentrate, non una sola. So all the values of bending strength that we will find, that we will meet in this course and from the regulation, will all be based on experiments carried out according to these requirements that I just mentioned. Is this concept clear? This is quite complex. So, on my own, I have to say, I have to play a little bit of time. In fact, I changed several times these slides. Today, well, this year I did also this sketch on the blackboard because perhaps it's easier to follow if we do slowly on the blackboard rather than on the slides. But now, I really invite you to read slowly through the slides to understand better. I mean, if it's clear what we said so far, also the reading through the slides shouldn't be so difficult. Because this is a little bit perhaps more precise. If you want, we can see quickly. But the idea is exactly what we said before, basically. So, you see, this is the failure point. And then, of course, we do this different derivation. 2-point bending moment. You see, in this case, if we compare, now we said before we said there was larger, smaller, etc. If you look at this example, in this case, this specific case, we can demonstrate that the FM2, so by testing the same specimen with 2-point rods, we would get a strength, an apparent strength FM, which would be 2/3 of the strength that we would get with this load configuration. 2/3, so it's a huge difference. 33%. That's okay. And then, now just go fast because to me it was interesting this part here. This one you can see on your own. And then you can see if I test, like in this case, only the left half, I will get a certain value of strength, higher. If I test only the right half, much smaller, because then you can get this difference in between. And so you see, different results are this conclusion, are obtained from the different load configuration, different lengths. Therefore, module rupture, which would be basically the strength, bending strength, should be evaluated always under 4-point bendings, ISO standard, EN standard. ISO is the kind of worldwide standard, and EN are European national standards. So, and the constant depth span depth ratio, 18. Yeah, the standard say, to be honest, constant, but also if you increase, it's not bad. The best thing would be to keep it constant. Actually, right constant, because you can also go above, but let's say that the standard, their standard set equal 18. Then, of course, if you do 19, 20, 29, it doesn't change so much. But if you want to be rigorous, let's be rigorous and give it like constant equal to 18. This should be the right way to evaluate the module rupture. Okay, so this is basically what we have just already discussed before. We don't need it now. Of course, this is for your notes, but it's basically what we said before. So we don't need to go into detail about this. And you see on clear specimens, so specimen without defects, strictly speaking, the bending moment will be in between the compression and the tensile strength. Instead, on structural size timber, the bending moment is between compression and tension, but they swap, you see, because in the structural size timber, the compression strength becomes higher than the tensile strength. So in the end, if you want to remember, this is a very simple way. The bending strength of some timber will depend on the probability to have a defect or not in the most stressed part of the cross-sectional area. What are the most stressed parts of the cross-sectional area in the bending member? The outermost fiber. So the idea is that, in this case, the strength, the bending strength will depend on the probability to find a defect in the outermost part of the cross-section. Note that this situation is completely different from tension. In tension, the stress distribution is uniform. So in this case, the tensile strength will depend on the probability to find the defect where? In which part of the cross-section?
The same.
Everywhere. It's exactly the same, everywhere. So in this case, the nodes can be here, there, doesn't make any difference, because we are talking about the strain distribution, uniform strain distribution. Well, instead before, it was different whether the defect here or close to the fiber. So this concept basically justifies why the tensile strength of a member in general is lower than the bending strength of the member. Why is lower? Because the probability to find a defect everywhere is higher than the probability to find a defect only on the outermost fiber. Clear? Quite clear. Clear? No? Probabilità di trovare un difetto solo qua, probabilità di trovare un difetto solo qui o qui, è più bassa che quella di trovarla tutto. Giusto? E quindi, so for this reason, a defect will affect much more the tensile strength than the bending strength. And now we stop for a break. And then this is the reason why the bending strength of some timber is usually, always, higher than the tensile strength of some timber. And usually smaller than the compressive